Hello! In this tutorial, we will be simulating laminar flow inside a custom cylinder. We will walk through creating the mesh, setting up and running the case, and interpreting the simulation results. To begin, we will be creating our STL file. I'll be using FreeCAD, but you can use any CADing software that you'd like Onshape. The only requirement of your CADing software is that you have to be able to export your mesh as a ASCII mesh. Anyways, to start with, we're going to create our cylinder. So I'm just going to click cylinder. And you can make your cylinder whatever dimensions you'd like. I would advise against creating a cylinder that is too short. But if you're not sure what dimensions you want to use, you can just copy my dimensions. So I'll be making a 200 millimeter radius and 200 millimeter tall cylinder, as you can see. And my cylinder will be running in the Z direction. So it's standing up and down, standing on top of the XY plane. Next, we're going to export this mesh. We'll be exporting it as an STL mesh, like this. And then we're going to create new. We're going to open our mesh. Go to this mesh toolbar here, and right click, export mesh, and make sure you export it as an ASCII STL. And you can name it whatever you like. I'm just going to call mine cylinder, like so. And now we have our cylinder. So just delete this. Okay, cool. We have our cylinder. Now we have to edit our STL file. The first thing I want to do is edit the regions of the STL file. So if you go into the STL file like this, if you just open it up, you'll just see a bunch of numbers. Basically, these numbers, these vertices, 3 vertices make up a triangle, right? And these triangles make up the surface mesh. So you can sort of visualize this if I just remove one of these triangles. So I just delete this. And then I go into ParaView. So I go into ParaView. And I open up my, go into ParaView and open up my cylinder. We should be missing a section. So you can see right here, we're missing a, well, this is a triangle, but I know it's kind of hard to tell, but this is a triangle that we're missing. So we've essentially created a hole in our mesh by removing that section. And this hole is described by this set of coordinates here that I've removed. Anyway, our goal is to rename the inlet and outlet sections. So for me, my inlet is going to be here. We're at the origin. So this is essentially the XY plane. And then my outlet will be this side right here. This is essentially the Z equals 200 millimeter plane. So in terms of millimeters, this would be Z equals 200 right here. That plane would be the outlet. So what I'm going to do is scroll through my STL file and look for a bunch of Z coordinates in a row that are either 0 and 200. Because, and this is where it's important to know your geometry, if I see a bunch of Z coordinates in a row describing, like a bunch of Z coordinates with 0, there's a good chance that those Z coordinates and those triangles are describing the inlet. And likewise, if I see a bunch of Z's describing a 200, a bunch of Z coordinates with a value of 200, that is likely to be describing the outlet. So you could probably create a software to do this for you. I'm not very good at coding, so I mean, I just scroll through it, but with a simple geometry like this, it's not too hard to do it manually. Okay, so you can see here, we've got a bunch of zeros in a row, right? 0, 0, 0, 0, 0, 0, all the way down. So I can probably guess that these coordinates are describing the inlet. So what I'm going to do is n solid cylinder. So I'm going to call the rest of the cylinder just cylinder. I'm going to start a new region called inlet. And now I'm going to scroll down until those zeros stop. So all of these vertices right here are describing the inlet. Right? Z coordinate of 0 is describing the xy plane. Okay, here, as you can see, we've got a bunch of 200s now. So I can guess that these 200s are describing the outlet. So I'm going to end the inlet region, start the outlet region, and then you can see here's the end of our file. So this is the end of the outlet. And I'm going to go back up because right now it's called unnamed cylinder. I'm just going to call it cylinder. We have three regions. We have the inlet, we have the outlet, so those are the top and bottom caps of the cylinder. And the rest of the cylinder, I just called it cylinder, but you can call it whatever you want. If you go into the command terminal, let me just get my Linux going. If you run this command, surface check, and then the name of your STL, this will tell you your region. So you can see we've got three regions: cylinder, inlet, and outlet. And this command will also tell you if there's any holes in the geometry. So let me just real quick, again, remove this first triangle right here. If I remove this command should tell me that, hey, you've got a hole in your geometry, and which is obviously not good because you don't want like fluids leaking out or whatever. But let's run this command again. You can see here we've got surface is not closed. So you can see that it detected that we created the hole. So make sure you run that command. Just make sure you didn't delete something that you shouldn't have. Another indication that you've successfully changed the region is if you go into ParaView and open up your STL. So just reopen it. You should have three different colors. So you can see our inlet is white, our outlet is red, and our cylinder, the rest of the cylinder, is just blue. So that's a good indication that you've changed your region successfully. Now, if we look into this data access grid, you can see that our cylinder is 200 units tall. Now, this would depend on your CADing software. My FreeCAD is set in millimeters. So in FreeCAD, this was 200 millimeters tall. But OpenFOAM reads every unit in SI, so this will become meters. So OpenFOAM will read this as 200 meters tall, which is obviously not what we want, right? That's way too tall. So we need to scale this STL down. We can do this using this command, surface convert, the name of your STL. It was going to create a new STL, so I'm just going to call that one capital cylinder.stl. Clean, and then scale, and then this will be your scale factor. So I'm scaling from currently in millimeters, trying to go to meters, so I'm going to scale down. And there we go. So now we have our new STL file. So if I remove this, look at the new one, now you can see we're in terms of meters. So this is 200 millimeters tall, which is 0.2 meters. So that's what we want. And now our STL file is ready to be meshed. So that's all. Okay, so the next thing we need to do is set up our case. So what we're going to do is go into OpenFOAM, go into tutorials, incompressible, simple foam, and motorbike. So this will be the case we'll be using just copy over the 0 constant in system file and copy that into your working directory. So like this. Okay, so let's see what we've got. We don't need any of these. We only need pressure and velocity, so we can delete everything else. Oh, well, guess we can't delete that. That's okay. And we'll rename this into our 0 folder. Okay, that's fine. Okay, there's a lot of things here. So we only need some of these. So I'm just gonna create a new folder because there's a lot of things in there. Call this system.original. Create a new system folder, and we'll take what we need. So we need block mesh, control dict, decompose par, FE schemes, FE solution, mesh quality dict, SnappyHexMesh dict, and surface feature extract. All we need from that. Paste it here. Next, open control dict, and we can delete these functions because we don't need them. Next, go back into constant, but take your STL. So I'm using the capital C STL. This is the scaled down version, remember. We're going to create try surface and paste our STL inside. And okay, so now we can finally start working on our block mesh. So this is essentially a background mesh from my understanding. I'm not an expert on meshing. But let's open up our block mesh dict. Okay, so essentially these vertices are describing the coordinates to a cube, I believe. Yes, this is a cube. Now we would like our cube to encapsulate our STL file. So again, this is where it's important to know your own geometry. So here is our STL. So we want to create essentially a box that will surround our STL, leaving a little bit of space on every side. So yes, let's start with the z-coordinate because, well, let's start with the z-coordinate. It's probably the easiest. So our cylinder is 0.2 meters tall, right? 200 millimeters. So let's make our box 0.22 meters tall. And then we'll leave a little, so that will create a 0.02 millimeter gap at the top, right? At the bottom, we'll create that another same 0.02 meter gap, right? Because our cylinder is sitting on the XY plane, like this. Now, in terms of X and Y, at the cylinder, so the radius in the X and Y direction are the same. They are both it's a 2 millimeter radius, so that would touch the cylinder. So let's do like 0.003. So this will leave a 1 millimeter gap between the block mesh and cylinder. So I'm just gonna change all of these into 0.03. Now we save our block mesh. Now down here, because we defined our inlet and outlet in the STL itself, we don't need to define our inlet and outlet in our block mesh. So we really don't need any of this. What I will do, however, is just create one boundary called wall and just put everything in there. So let me move that out. So just rename this to wall. And then I'm just going to take all the vertices and describe and put them all here, because these blocks here are essentially describing, or sorry, these coordinates here are describing one side of our block mesh. So just take all the sides in the block mesh and put them here, if that makes any sense. So you should have 6 for 6 sides, right? Yes. Okay, and we can remove all of this. We don't need this anymore. Okay, nice. So if we go back into our terminal and block mesh, okay, and now we can run this command to see our block mesh. So if we close this pair view, go into our working directory, open OpenFOAM, apply, you can see we've got a nice little block. I think, let's see, I might have made my block a little too small. Yes, okay, looks like I messed up the radius, that's fine. They always change. I think it's off by magnitude 10, right? Yes, because it was 20 millimeters, not 2 millimeters. So we'll do like 2.5. Yeah, so I messed up the dimensions, but that's fine, right? Let's see here. Yes. So now, so the radius of the cylinder is 0.02. So I'm going to make my block mesh 0.025. That will leave a 0.005 or 5 millimeter gap. Yes. So you can see, yeah, I'm not very good at this. But it's okay, because we can always fix our mistakes in the OpenFOAM world, usually. Okay, so if we just rerun block mesh, and then we refresh, hopefully, yes, it will now encapsulate our cylinder. Very nice. Okay, slight setback, but that's okay. So now our block mesh is done. Actually, I lied. We need to adjust the grading. So you can see here, these numbers right here describe the grading of the mesh. And what I mean by that is how refined it is. In the X, the 20 describes the X, the 8 describes the Y, this third 8 describes the grading in the Z direction. So essentially what this is saying is 20 cells, it'll take the X direction, so let's see, let's see where X is. X is to the left. So you can see here, there should be 20 cells across in this direction right here. We would like, you can make it as fine or as coarse as you'd like. I'm probably gonna do like, I don't know, we'll do 20, 20, 10, sounds about right. But essentially what this is saying is 20 cells in the X direction, 20 cells in the Y direction, and 10 cells in the Z direction. And whatever grading you do, make sure your X and Y are the same for this case. And you'll see why later when it comes to post-processing. Anyways, when run block mesh, we can refresh. You can see now our X and Y direction is about the same. It's graded evenly in both the X and Y direction. So our block mesh is done. Now let's go to surface feature extract. So in system, surface feature extract dict. Basically, I don't know what this does, but yes. This number, you can increase it to capture more of the STL. So basically this is more refinement, and the smaller this number, the less refinement. And now we can we're gonna make this 180. Go back to our terminal, type in surface feature extract. Oh yes. Make sure you also change this, because this is taken from the motorbike case, so it has motorbike.obj. We don't have that, we have cylinder.stl. Okay, nice. And again, this is not going to run if you don't move your STL file into tri-surface. So make sure you do that. Otherwise, this is not going to work. And now we can finally start working on our SnappyHexMesh. So let's open that up. SnappyHexMesh dict. Okay, so the first thing I'll do is go and search for every instance of motorbike and replace it with cylinder, because we're working with cylinder, not motorbike. And this .emesh file was created through surface feature extract. You can check that by going into constant. So yeah, you can see that surface feature extract created this extended feature edge mesh and the poly mesh. And if we go to try surface, you can see we have our cylinder.emesh, so that's what this is referring to. Call the cylinder. Okay, cool. Change everything into cylinder. Nice. The first thing we need to do is this refinement box. This essentially just tells SnappyHexMesh which areas to refine. So we would like to refine the whole STL, so this refinement box should describe the whole STL. And you can use your block mesh for reference here. Essentially, this min and max describes a box. So for us, would be like negative 0.01, 0.21, 0.023, and same in the x direction. Essentially, what this is telling SnappyHexMesh is, if you go into ParaView, it's basically telling SnappyHexMesh that we want to refine from, let's see, I forgot what I made already. I believe it was negative 0.01, so that'd be like this point right here, I think, to all the way to this point right here. So we're going to rename this to fluid. You can name this whatever you like. And sort of just follow me here. We need to define the regions that for SnappyHexMesh. So remember our region for inlet, outlet, and cylinder. So call this inlet. like so. And let's close this. So we're missing a curly bracket here. Close that one. Move this one. And close the fluid curly bracket. Okay. Cool. So that's set up. Our next step. So yeah, you can read through all of this if you'd like. I'm not going to go too much into depth into all of the different tools you have for SnappyHexMesh. There's a lot of them. This level controls refinement. The bigger the number, the more refined your mesh will be. We're going to keep it at 3 for now. We might adjust that later. Okay, here, refinement surfaces. Okay. So we're going to reference those regions that we just defined over here, down here. So, okay, so we have fluid. We'll make this 2 and 4. We might adjust this later. Change this to region. Let's see. So yeah, here's where we reference the regions from above. The inlet and outlet will be type patch, and the cylinder will be type wall. So yeah, these levels right here essentially refer to how much more the block mesh gets refined. So if the mesh is less refined in this feature angle, then the mesh gets and this part should be done. Just remove this. Okay, this part looks good. Again, I believe this number, the smaller it is, the more refined it is. Again, you can look online for more information. Make this 3. So yeah, the bigger this number is, the more refined it is. So yeah. Okay, location and mesh. This is very important. So essentially, the location mesh specifies a point. If this point is inside your STL, then SnappyHexMesh will mesh inside your STL. So the scenarios where you would want to do that is like for fluid flow, like for what we're doing, we want to mesh inside the STL. So we want our point to be inside our STL. If the point is outside the STL, then that would be for like a drag simulation or like airflow simulation. And SnappyHexMesh would mesh outside of your STL. So we want the location and mesh to be inside. So again, this is where it pays to know your geometry. Just pick a point inside. So this is the block mesh, but so you want to pick a point that's ideally towards the center. So we're probably going to pick a point along the center axis, which would be the z-axis, really. and our cylinder is 0.2 meters tall, so let's pick in the middle, 0.1 meters. So that means our what's it called? Our location in mesh will be 0.1, which would be this point right here along the z-axis. But yes, it's very important that you pick your location in mesh inside your STL. So however your cylinder was orientated, if it's the same as mine, then you can just copy my location in mesh. But if it wasn't, then make sure it's inside the STL. So it'd be like in here. Anyway, that should be it for now. Layers, we don't necessarily need layers, so we can turn this to 0. And that should be it for SnappyHexMesh. So let's go to one final thing we have to set up is the decompose part. Dict. So okay, so change this to Scotch. We don't need this. A number of subdomains. So this is the number of processors that you have in your computer. So you can check that by going to Task Manager. I'll be going with 6, but it depends on the. Okay, so our next step is to edit our initial pressure and velocity files. So if we go into 0, we open both of these up. Okay, so the first thing we need to do is remove any reference to the include. This was a part of the motorbike case, but we won't be using include, so we can just remove it. Okay. Next, we need to change motorbike group to cylinder. Like this. Next, we need to change this $sign pressure was referring to something inside the include folder, but since we removed it, we have to change this as well. We'll just make this 0. Let's see, make this 0. And we need to reference our block mesh so it doesn't get mad at us. So I'll change that to walls, and this pressure file looks good. Going on to velocity, again, remove any reference to include. So don't need any of this. Make sure you control S, of course, as you go. Okay. And again, this flow velocity is referencing something inside the include folder, so we have to remove it. We'll just replace it with 0, 0, 0. Let's see. Let's define an inlet. And we'll call it type fixed value. So this will apply fixed inlet velocity to the inlet. And we'll call it, and it'll have a value of, so again, this is where it's important to know your geometry. My cylinder is running in the Z direction with the inlet on the XY plane and the outlet on the Z equals 0.2 plane, which means flow will be flowing upwards. So we want our inlet to have a positive, it needs to have flow in the positive Z direction. And we will set a inlet velocity of 0.01 meters per second. Okay, change this out, type outlet to, we can leave this actually, leave it as inlet outlet. delete this. And we don't have a lower wall, we can just change this to walls. And we'll be applying a no slip condition. So this, and don't forget your semicolons, otherwise you're going to get an error. And this will be cylinder. So yeah, this cylinder is referencing the cylinder right here. So this one's lowercase, it's not referencing the STL. Otherwise it would be capital. Okay, so now we can run the decompose par. Let's see. Looks like I forgot curly brackets somewhere. Yes, right here. Okay, let's try again. Okay. And now we can type mpyrun number of processors. So this is 6 for me, but this will change depending on your computer and your decomposed project. SnappyHexMesh overwrite parallel. Okay, well, SnappyHexMesh crashed my computer, which is always amazing. It tends to happen. I just restarted my computer if that happens to you. Anyway, let me just run everything again. So block mesh, surface feature extract. You probably already did this if your computer didn't crash. Decompose part, and now mpyrun number of processors. So we have 6 processors in this case, but again, it depends on what you used in the decompose project file. SnappyHexMesh overwrite and parallel, and you let SnappyHexMesh do its thing. Okay, so you can see our SnappyHexMesh is done running. Next, run this reconstruct parmesh in the content folder, and then we will run the check mesh. This will return these important statistics of your mesh, like skewness and concavity and things like that. It basically tells you if your mesh has any errors. So you can see we have 264 faces with concave angles. This is fine. Generally want to keep this number as low as possible, but we'll live. Okay, so we are almost ready to run our simulation. Just need to make some final changes. The first thing we need to do is edit our control dict and FV schemes. So open up control dict. So these are the settings from the motorbike simulation, but we're not running the motorbike simulation, so we need to change these. We'll make our end time 1, our delta t 0.001, and everything else should be good. Next, we need to edit our FV solution. So we only need pressure and velocity, so we can take out everything that isn't pressure and velocity. These are all turbulent terms that we don't need. Okay, and finally we go into our constant folder, turbulence properties. Again, we're not using turbulence properties, so we can take these out. We don't need these, and we're going to set our simulation type to laminar because we are running a laminar case. And we should be good to run our simulation now. Type simple foam, and we let our simulation do its thing. Okay, so before we get to post-processing, I think it's helpful to gain a basic understanding of the fluid physics behind our simulation. The most important number to know is a fluid's Reynolds number, which is a dimensionless quantity that describes the fluid's flow pattern. Reynolds number is given by the following equations: density times flow velocity times diameter divided by the fluid's dynamic viscosity, and you can rearrange this equation into this equation, flow velocity times diameter divided by the kinematic viscosity. And this equation is a bit more useful to us because we are able to directly change kinematic viscosity through the transport properties file. As you can see that Reynolds number is directly proportional to flow velocity, right? And inversely proportional to kinematic viscosity. Now, generally speaking, a Reynolds number above 2000 indicates that flow is turbulent, and Reynolds number below 2000 indicates that flow is laminar. For laminar flow, think of water coming out of a faucet. It's streamlined and very easy to predict. We can confirm our flow is laminar by taking a line scan across a cross-section of our pipe and plotting the velocity values, and this graph should form a parabola. Turbulent flow, on the other hand, is unpredictable. Think about fluid coming out of a spray bottle. Now, we are aiming for laminar flow, meaning we want a sufficiently low inlet velocity and high kinematic viscosity to get a Reynolds number below 2000. There's one more part to this equation, and that is the entrance length of the pipe, which is given approximately by the equation 0.05 times the Reynolds number times the diameter of your pipe. The entrance length describes the length it takes for fluid to develop. In our case, the length it takes for our flow to become parabolic. This is why earlier in the tutorial I cautioned against a pipe that is too short, because if your entrance length is longer than your pipe, your flow just doesn't have enough space to fully develop and become parabolic. And by that same token, you don't want your line scan to be too close to your inlet, since your flow may not have developed at that point. If this happens to you, you can try adjusting your Reynolds number to be lower, again by lowering the inlet velocity or increasing the kinematic viscosity. But I wouldn't lower the Reynolds number to be lower than 10, because in my experience, OpenFOAM really struggles with super slow flow. So if we wanted to calculate the Reynolds number and entrance length for our simulation using the properties I set, we'll use this equation first. So flow velocity 0.01 is the inlet I chose. The length or diameter is 0.004, I believe. Or no, it was 0.04, sorry. 4 centimeters, 40 millimeters. And our kinematic viscosity is 1.5 times 10 to the negative 5, or the kinematic viscosity of air. And if we just type this in, we see our Reynolds number is 26.666667. So you can see we've got a relatively low Reynolds number, right? The requirement is for the Reynolds number to be below 2000. But it's not so low that OpenFOAM is going to struggle because our flow is too slow. And if we wanted to calculate entrance length, we would just take this number times 0.05 times, again, our diameter. And you can see our entrance length is 5 centimeters or 50 millimeters. So you can see that up until here, until this line here, our flow is developing. And anything past this point, our flow is fully developed. which means if we were to take our line scan anywhere before this 5 centimeter mark, we wouldn't get a perfect parabola, even if our simulation had fully converged. We would need to take the line scan from this 5th centimeter onward. And I can show this right now, actually. So if we were to take a line scan across, we'll do that at 0.03, for example. So this is before the flow is fully developed. You can see this parabola is blunted, which is a pretty clear indication that the flow is still developing. And this is a bit more apparent if I do even earlier on in the pipe. So this is just 1 centimeter in, which would be around here. You can see the line scan. You can see doesn't resemble a parabola at all. But if I go further into the pipe, I'd say halfway into the pipe or 10 centimeters in, you can see the parabola is a lot nicer. And you can see that this parabola won't change even if I go another 5 centimeters, because by this point we're past the entrance length, our flow is fully developed. You can see the change is pretty negligible. So yeah, this is where it's important to know Reynolds number and entrance length, because if your inlet velocity is too high or your dynamic viscosity is too low, then you're going to have turbulent flow and you're not going to get this nice looking parabola. Or if your pipe is too short, or you're taking your line scan too early onto the pipe, you're going to get a blunted parabola, or just because you're taking a scan across a region of the pipe where the flow isn't fully developed. So I hope that made some sense. Anyways, on to the post-processing. Okay, as you can see, our simulation is done running. Pretty good indication that your simulation results are alright are that these residuals drop to very small numbers, usually to the -6. So you can see we're closer to the -10 range, which is very good. We can now look at our results in ParaView. So open up ParaView here. And here is our simulation results. Okay, so in order to compare our simulation results to the theory, we need to graph the velocity across a dimension, either the x or y dimension in our case. In order to do this, we first go to Filters, Domain, Data Analysis, and Plot over Line. And it shouldn't matter if you choose the x or y direction. We'll choose the y direction, so we're going to hold x to 0, and we'll vary the y across the radius, or diameter, I guess. And we'll pick a pipe pretty far up the pipe. Depends on your entrance length, but we'll do 0.18. So our whole pipe is 0.2 meters, so 0.18 is like 90% of the way up, I think, if my math is correct. And you can see we've got a very nice looking parabola here with a vertex at roughly 0.02 meters per second, and it should be towards the middle, which should make some sense because the middle of the pipe should be the fastest, right? The edge of the pipe should be 0 because we have a no slip condition. You can see it's at to the -5, which is basically 0. Yeah, so we'll go to a spreadsheet view and export. So we'll call it like line scan. I already had one test run, but we'll just replace it. And I'll see you in Google Sheets because I'm too broke to afford Excel because it costs money for some reason. Okay, so we're here in Google Sheets. So we're going to wait for this to take 7 years to load. While it loads, I just want to explain the equation we'll be referencing. So we're going to graph our equation against this equation right here. U is velocity, G is pressure gradient, mu is the kinematic viscosity. Big R is the radius of your pipe, and little r is the varying radius, like your x value, your input. And we're going to see how well it matches up against this equation. So since this is still loading, in fact it's not loading at all. I'll first teach you how to calculate g, which is just dp over dx. So if we go over to power view here, and we'll look at pressure. So using this nice little handy legend, I guess, scale, basically you could probably like take a line scan across and average it, but I generally just eyeball it. Probably not a very good idea. You should probably take a line scan like I did with the velocity, but I'm very lazy. And I like to treat this bottom part as 0 because it theoretically should be 0. To the -6 is practically 0. So that looks about like between 0.001 and 0.0005. So we'll call dp 0.005, or 0.0005, sorry, 3 zeros, 5 to the -3rds. And our dx is just the length of the pipe, which is 0.2 meters. So we'll do 0.0005 divided by 0.2, giving us 0.0025. That is our g value. And then divided by 4, and then divided by our kinematic viscosity, which we set to be 1.5 to the -5, which is, I believe, the kinematic viscosity of air, I think. Could be wrong on that. And that will give us 41.66667. So, okay, after 7 years, my Google Sheets decided to finally load. So I'm gonna insert some columns because I don't like working in a cramped spreadsheet. The only thing we really care about here is the magnitude of velocity and the varying r. So we're gonna take this. This will be our x, our velocity. This is our simulated velocity, and then our theoretical velocity according to the equation. Whatever French, I don't know if that's French or not, but whatever. So remember that this term out in front, g over 4 mu, just simplified to 41.66667. So we'll do that times our radius squared, right? Big R is our radius, and little r is the radius that's varying, so that'd be this column n, like so. And I guess we'll autofill it. I didn't know they had that, but the more you know. And we'll insert a chart to see how well we match up. So you can see that we're not perfectly matching up, of course. It's a simulation, but it's not, orders of magnitude off, which is a good thing. Another thing you can do here is check out the r squared of the simulated results. So if I can figure out how to use Google Sheets, I think it's something like this. Well, obviously the r squared of this equation is going to be quadratic because this is a quadratic equation. But we care about the simulated r squared. Okay, so you can see they're both 1. They're both perfect parabolas, which is nice. Now, of course, they're not matching up perfectly. It's a simulation, but, this is to be expected. One thing you can do is use a parabolic inlet velocity. So I'll show you very quickly. I used this in the previous case. So yeah, you can use this inlet velocity, which is essentially, instead of being uniform, it inputs the velocity initially as a parabola. And this, in theory, will get you a better simulation result in terms of the fact that it'll be closer to the theory. So using this inlet boundary condition as opposed to the uniform boundary condition will give you a simulation result that is closer to the theory. It's still not going to give you exactly the theory because it's a simulation, right? But it gets you closer. So if you want to copy this and implement this, you can, but I don't. This is more of like a cherry on top kind of thing. Yeah, so that's the simulation. If you have any questions or comments or anything, if you're confused, you can leave them in the comments. If you found this helpful, feel free to leave a like or dislike or nothing at all. Doesn't really matter to me as long as you found the video somewhat interesting and helpful. But yeah, maybe I'll do another tutorial, or maybe I won't. Depends on how lazy I am. Okay, bye.